Have you ever really looked at the world around you and wondered why things are the way they are? I mean, why is a window clear, but a wall is not? Why does a metal spoon get hot in your coffee, but the wooden handle stays cool? Well, there's a science that explains all of this, and it's called solid-state physics. It's basically the secret rulebook for everything solid.
So let's start with a really simple question that gets right to the heart of it. Why is a diamond, super hard and totally transparent, while a piece of copper is shiny, soft, and you can bend it? They're both solids, right? But they couldn't be more different. The answer, it turns out, is hiding deep inside, down at the atomic level.
To find that answer, we've got to zoom in. Way in. And the first big clue we find when we get down there isn't chaos or randomness. It's the complete opposite. It's an incredible, almost perfect sense of order.
You see, most solids are what we call crystalline. And why is that? Well, it's because nature is fundamentally efficient. It's all about saving energy. And forming a perfectly ordered, repeating pattern is just the lowest energy, most stable way for a bunch of atoms to hang out together. It's like they've all found their most comfortable chair to settle into. And we call this perfectly ordered arrangement the crystal lattice. Just picture it, a massive, three-dimensional grid that repeats itself over and over again in every direction. The atoms are sitting at each intersection of this grid. This lattice, this is the fundamental scaffolding. It's the blueprint that determines pretty much everything about the material.
Okay, so we've got the scaffolding, but what's holding it all together? What's the atomic glue that keeps all those atoms locked into place? This is our next big clue, so let's check it out.
Turns out, this atomic glue comes in a few different flavors. Two of the most common are ionic and covalent bonds. An ionic bond, like the one in table salt, is kind of like a transaction. One atom literally gives an electron to another. It's a give and take. But a covalent bond, which is what you find in a diamond, is more like a partnership. Neighboring atoms share their electrons, and this sharing creates an incredibly strong, super rigid connection between them. Which brings us back to our piece of copper. See, metals have their own special kind of glue, the metallic bond. In this case, the outer electrons aren't just given away or shared between two atoms. No, instead, they're all pooled together. They're donated to this collective sea of electrons that just flows freely around the whole structure, holding this rigid grid of positive ions together.
And here's the crucial part. The kind of glue you use directly determines the properties we can see and feel. Those ionic bonds, they tend to create brittle materials. The ridiculously strong covalent bonds in diamond, we're talking a binding energy of 7.4 electron volts. That's what makes it the hardest natural substance. And that sea of electrons in metals, well, that's what allows the atoms to slide past one another, which makes metals bendy and ductile. Oh, and all those free-roaming electrons make them amazing conductors of electricity.
So, let's recap. We've got the structure, the lattice, and we've got the glue, the bonds. But to really truly solve the mystery of diamond versus copper, we need the final, and maybe the deepest clue of all. It's not just about where the electrons are, it's about what they're allowed to do. There are rules of the road.
You see, inside that crystal lattice, an electron can't just have any old amount of energy at once. It's kind of like being in a skyscraper where you can only stand on the floors, not hover in between them. These allowed energy levels, these floors, are grouped together into what we call energy bands. And this idea, as simple as it sounds, is the key to everything.
Let's try an analogy. Think of it like a highway system for electrons. So first you have the valence band. This is like a crowded local street, bumper-to-bumper traffic. All the electrons start here, stuck in place, down to their home atoms. Then there's the conduction band. This is like a wide-open multi-lane expressway. If an electron can get up here, it's totally free to zip around and conduct electricity. But here's the catch. Between them is the forbidden gap, an impassable barrier. An electron can't exist in the gap. It has to gain enough energy to make the entire jump at once.
And the size of that gap, well, that determines everything. In an insulator like our diamond, that energy gap is huge. It's a massive canyon. It would take an enormous amount of energy for an electron to make that jump, so it basically never happens. Now, in a metal, like our copper, there is no gap. The bands actually overlap. The local road merges right onto the expressway. It's always open for business, which is why metals conduct electricity so well. And what about semiconductors, like silicon? Well, they're the interesting case. They have a small, manageable gap. Just a little energy boost is enough to get some electrons jumping, and this in-between property is what makes them so incredibly useful in all our electronics.
So, there you have it, our complete toolkit,
the structure, the bonds, and the energy bands. With just these 3 keys, we can unlock the secrets of not just everyday stuff, but some of the most bizarre and amazing materials you can imagine.
For example, magnetism. Why is a regular old piece of iron magnetic? It all comes down to the electrons again. In some materials, there's this weird quantum effect called the exchange interaction. You can kind of think of it like peer pressure for electrons. It strongly encourages all their tiny magnetic fields, their spins, to line up and point in the same direction. When enough of them do that, bam, you get a powerful magnet.
Or how about this one? There are certain crystals that literally generate electricity when you squeeze them. It's called piezoelectricity. This trick only works in crystals that have a slightly lopsided structure. They don't have a perfect center of symmetry. So when you put the squeeze on them, all the positive and negative charges inside get pushed to opposite ends of the crystal, and that creates a voltage.
And this isn't just some lab curiosity. You use this all the time. It's how old record player needles worked, it's inside lots of microphones, and it's even used to create ultrasound. Squeeze the crystal, you get electricity. And it works the other way too. Apply electricity and the crystal squeezes itself.
But maybe the most mind-blowing property of all is superconductivity. If you get certain materials cold enough, really cold, they enter a whole new state of matter where they conduct electricity with absolutely no resistance, no friction, no energy loss, just perfect, effortless conduction.
And I'm not rounding down here. The electrical resistance is exactly 0. If you started a current flowing in a loop of superconducting wire, it would just keep going, forever. It's wild. It happens because the electrons team up in pairs and start moving through the atomic lattice in this perfectly synchronized dance, which lets them glide right past all the atomic obstacles that normally cause resistance.
Okay, let's zoom back out. We started with a simple question about a diamond and a piece of copper, and we've journeyed all the way down into the quantum world of atoms and electrons. So, what's the big takeaway here? What does all this understanding actually give us?
Well, the crucial point is this. Everything we see and touch, a material's hardness, its color, its conductivity, its magnetism, you name it, it's all a direct result of this invisible dance going on at the atomic scale. The world we experience every day is built entirely on these microscopic rules of structure, bonding, and energy.
And the real power of this isn't just explaining why things are the way they are. It's predictive. Because we understand these fundamental interactions, scientists can now calculate what the most stable structure for a combination of atoms will be, and from there predict its properties, all before they even make it in a lab.
And that, of course, leaves us with one final, really exciting question. If we truly understand the rulebook, does that mean we can become the architects? Can we use this deep knowledge to design brand new materials from the atoms up, materials with any property we can possibly imagine? That is the bleeding edge of material science today, and it all starts with the principles we just talked about.